It's worth seeing this as, or taking a look at this as a different way, which is to look at it as, we're basically doing the same thing over and over again, right? We're taking f of xi times delta x. So we're going to save this for a second, all this loop stuff. And we're going to try to think of this as a matrix problem. Because we know if I had a vector of x's, I could find the cosine of all that vector of x's just by saying cos of x. We can use vector inputs. So one of the things we might want to do instead is use a sum or something like that, which are built into MATLAB. So what we can do here is maybe call our x's and make that, well, what is it? It's 0 to n minus 1 times delta x's. So this will be our vector approach. So this is all the x's together. So if I take 0 delta x's, 1 delta x, 2 delta x, that's going to be all my left-hand endpoints. And then what we can try to do, and if we've written our function right, it'll work, we can say here f equals, now we already used f, f values. And compute f at all the x's. So instead of doing a loop, which you have to go back and redo, this is another way we can try to do this. I'm going to run this and just make sure it doesn't throw up on us. Because vectors and scalars are different, and maybe we've written things out. Oh, we have. We're fine. So everywhere we had an x here, we had the right dot multiplication that we needed. And so what we can do at the end of the day here is do a sum and say q is equal to the sum of the f values times delta x. Because actually, I guess we can make it look the other way. That would be exactly what we have in our handwritten math side. Sum of f times delta x is exactly what we want to compute, because here it is, sum of f times delta x. So let's get MATLAB to do that for us. And if we do that, fingers crossed. Oops. That didn't work so well. Should be f, oh yeah, right, excellent catch. So xi was what we called it before, but now it's x. So we were doing the same thing again, actually. We were using the last point over and over and over again. So this should be f of x. Excellent catch. And if we do that, we get the same answer as we got before. Compare it with the right answer, so 2.3627 instead of 2.26. We're in the same ballpark. It's exactly the same calculation that we did last time. And it turns out this is more of a MATLAB thing than a general programming thing. But vector calculations tend to go faster. So if you're writing a program a year or two from now where you're doing big calculations, you can often speed things up, especially if it's the thing that you're doing most often. You can often speed things up by trying to think, how can I get this to happen as a vector instead of looping manually over things? So what I want to do briefly right now is trade this off and actually find the error. All right. So what I've changed here is it said n, and instead of printing what the actual value is, now we're going to talk about quality. So we imagine that the more intervals we use, the bigger n is, the more accurate our answer is. I just want to back that up with some evidence. And let's get rid of the exact answer here. And at the top, no, I don't want to put a top there. I'm just going to CLC, clear the screen here. And what we're going to do is run this a bunch of times with n being 10. Let's go to 100. And then we'll double it every time. And then 800, and 1600, and 3200. Lovely. Oh, so lovely. Hey, when I double the number of intervals, what happens to the error? Gets cut in half. Right. Well, that's handy to know because it means we can make some predictions. If the function is like this function, but it turns out if you have a nice smooth function like this, if I want to do twice as much work, or get the computer to do twice as much work for me, let's be honest, then I'm going to get an answer that has half the error, or twice as good is hard to say, but half the error. That's going to be useful because what we're interested in, again, is that trade-off between how much work we're doing and how accurate an answer we're going to get at the end. So that's the left-hand rule. Double the number of intervals, twice the work. we're going to take our error and cut it in half for these nice smooth functions. What we're going to see is, by just being a little bit smarter about how we draw our shape, in this case rectangles, if we get a little smarter about how we draw our shapes, we can get much better performance with very, very little extra work.